It's great. So let's get started, everyone. So welcome back. We're going to be talking about estimation today. So estimation in so I'm going to give like a perspective of this from probably and so statistics, but like if you were like so pitching money to like a VC or something, you'd probably call this machine learning or probably like AI actually. Well, so it's closer machine learning, so part of AI, but this is in some sense it's very similar to what you do in machine learning. And we'll also be talking about things like bias and variance as well here. So just a quick look at the schedule again. We are in the statistics part of the course. We did a very quick coverage of 3 chapters in the book on introduction to statistics. There's one thing I didn't quite finish in full, so coverage on the central limit theorem, which is really important. So I'll start with that in today's lecture, but it's in the notes and the slides from Tuesday. Don't forget there's a quiz as always, and then homework 5 is due on Tuesday next week. If you haven't picked up a copy yet, there are copies up front here. So okay, all right. So estimation, so bias and variance. Before we get into this, well, I want to talk about something very important from statistics, central, limit theorem. All right, and we went through most of the premises of this, but I didn't feel like I wrapped it up in a bow, so I'm going to kind of go over this again. Probably also a good thing to remember for the quiz. Okay, and so this will also allow me to review a lot of the core stuff we talked about on Tuesday, which probably went pretty quick because we covered a lot of material. All right, so the start of it is we are going to assume we have some random variables x1, x2 up to xn. Okay, and these are all going to be IID from the same distribution, right? So if they are IID, then they have to be from the same distribution. That's what the identical means, and the other I means they're going to be independent. All right, so we have a bunch of random variables that are from the same distribution and they're independent observations from each other. And so this is kind of the basic premise of statistics. We're thinking about, this is a random variable, so we haven't done any actual observations yet, but we're thinking about potential observations, and we're doing a repeated process of n of these observations. All right, and we know 2 properties about it. We know that the expectation of each xi is equal to mu. So this is, some parameter mu. This will show up in these, the result of the theorem, and these are identical, so it's all the same, right? And also we know that the variance of each of these xi's is going to be like sigma squared. Again, they're all the same. This has to be bounded less than infinity, okay? So there are some distributions that have a well-defined finite expectation, but the variance is not bounded. Those we can't use in this theorem. We haven't seen any of those in the class, but those exist. Okay, and then we want to think about this new random variable. I'll call this xn bar. Okay, this will be kind of a pretty common thing to think about. If I put a bar on the top of something, it often means I'm taking the average, right? So this is going to be 1 over n, sum of I equals 1 to n of each of the xi's, right? So I'm going to make these observations, x1 through xn, and then I'm going to take the average of all those observations. So, okay, this is kind of a very, somehow taking an average. Sometimes I'll define other functions I'll do, but this particular theorem is about taking the average of a bunch of observations. Okay, and the consequences of this, there are 3 main consequences of this. Okay, and we saw all these, but I didn't kind of wrap it and call it the central limit theorem. The first one is about, and they're all about this, this x bar n. The first one is the expected value of x bar n is equal to, so mu, right? We talked about this from the linearity of expectation. You just put the definition of x bar mu into the expectation and you factor everything out and and it turns out it's mu. The same as before. So the same expectation as before. Okay. So that's like the central part of the central limit theorem. So the next question is about the variance, right? Expectation and variance are kind of key properties we might want to look at. Okay, and the variance is going to be sigma squared divided by n. Okay, and so this is kind of what happens so the limit, that is n gets large. What happens when n gets large? The variance gets smaller. You're dividing by n, right? So you get smaller and smaller variance. This is becoming centralized around the mean, right? The expected value, the mean, that's still inside the distribution, but the variance, the expected deviation, the expected squared deviation, the variance is becoming smaller. Okay, and then the third one is that as n goes to infinity, so in the limit, then x or x bar n, so converges to the normal distribution with the mean of mu and the standard and the variance, right? We know what what those means and variances, right? It basically looks like the normal distribution. Okay. So this is typically how it's written. That's converging to the normal. It kind of looks like a normal distribution afterwards. Okay. I'd say that looks like the normal distribution is kind of, often one reason people cite why the normal distribution is important. We've seen it show up in a lot of places in this class so far. We aren't so done with that yet. But I think the real important thing, at least from the machine learning and data science perspective, is this one, that the variance is shrinking. It's important that that the expected value is the right thing. Okay, that's pretty important too, but that the variance goes down, and we kind of understand that rate. That it's, as we get more data, the expected square deviation is going down at this controlled rate we can understand. And this means as we get more and more data, we get a more and more accurate estimate. Okay, one last thing, there's another kind of way of writing this. Probably, when I write number 3, and this is often how it's written, this seems kind of strange to me, because I'm thinking about what this xn converges to, but at the same point as n goes to infinity. But if the sigma squared is going to be bounded, it's finite, then as n goes to infinity, that's going to 0. Which is kind of weird. So it's a normal distribution with the variance 0, and that's kind of like you're dividing by that later, and that seems kind of strange. Okay, so there's another way of phrasing this. I can also create this other random variable Zn, okay, and this is going to be xn bar, but minus mu, and now I'm dividing this by sigma So square root n, right? So this guy here, this is the standard deviation of xn bar, right? So it's the square root of the variance, right? So if I divide by it, I want to divide by something with the same units, right? The standard deviation is the same units, right? So I'm dividing by the standard deviation. If I look at the standard deviation of xn bar, right? If I look at the standard deviation of this guy here, right? Its standard deviation is going down at a rate of square root n, right? As square root n gets bigger, it goes down at a rate of square root n, but now I'm dividing by sigma divided by square root n, which actually means I'm multiplying by square root n, right, on the bottom here. So those square root n's cancel out. So I don't have anything that's going to zero now. Well, I actually do have something that's so going to zero. I mean, it's going to be, what is going to zero is the mean of the distribution, because I subtracted off mu, which is the expected value. Okay, so what I can claim now is that in the limit as n goes to infinity, that Zn will be distributed as a normal random variable with zero mean and standard deviation 1. Okay, so it's okay for the mean to be zero, right? If that's just a real value, it can be negative, it can be positive. Zero seems like a good, spot in the middle. And now the variance is 1, which is kind of the kind of a reasonable thing for the variance to converge to now, right? So this is a little bit easier to kind of to think about kind of rate of the central limit theorem. So this is kind of this would be kind of like 3, like an alternative version of 3, right? Instead of converging towards something where the variance goes to 0, you're converging to something where this variance goes to 1, which makes more sense. All right, so this is a really important thing. It says as we get more data, we get more and more accuracy, right? As we get more and more accuracy, so we can look at the expected value of the average and say that's going to very likely be close to the true mean of the distribution, right? So this will be a useful thing, and this is going to be the power behind estimation, right? We're going to do estimation, and this will tell us what is going to be a good estimator. Okay. So this central limit theorem, probably, if you remember, like one of the top 5 things to remember, from this class after kind of the basic definitions, like what is probability, what is the random variable, stuff like that, central limit theorem is really important. Like Bayes' rule, really important tool. Central limit theorem, like a super important tool. Okay, so this is a kind of a really important thing to remember. All right. Yes. So someone asked me before class, is anything in R going to be on the final? It's possible. Is central limit theorem going to be on the final? Probably. Okay. It's one of those things I think is like really important from the class. Yeah. Yeah, and this is a particular way of quantifying that. Okay, as you get further along in like machine learning classes and stuff, or probability classes, you'll see different ways of quantifying how as you get more data, it gets more accurate. This is kind of the bare bones version of it. This is kind of the simplest, most general way to say something about it, right? There are kind of many variations of the central limit theorem. We saw, for instance, like if the distribution F was exactly a normal distribution, then you can say something specific about the distribution of that X bar N is drawn from. It's more specific, right? You can say other things. If I know something about the distribution F, I can say something more precise about how fast it's converging other than just the variance, for instance. Or how close it looks to the normal distribution. How do I describe what so converges means? I didn't really define converges here, and it's a functional convergence, and I didn't really define that carefully, right? But this is kind of the key principle of what's going on. Okay, that as I get more data, the variance is going down at a rate of n, the standard deviation is going down at a rate of square root n, and the expected value is staying the same if I take an average, right? Those are really the key principles here. And this is a very general property, assuming I've got some, some data observations which are IID. Yeah, all right, so there's a lot going on here that we build up over the semester, but you should be able to understand this theorem at this point, and we'll see some implications of it we'll see some how this is useful over the rest of the semester. Yeah, so, okay, so it's not just this, but we'll kind of see some consequences of this. Okay, great. So to get into estimation, what we're really we need to first think about parameters of a distribution. Okay, and for this, we're generally going to be using continuous distributions. The central limit theorem holds even if the distribution is not continuous. You could have a discrete distribution, and then you average a whole bunch of them, and it will converge to the normal distribution, which is continuous, right? It's kind of wild, right? But for discrete distributions, but what we want to deal with continuous distributions now, because they're usually described by a small number of terms. These are the parameters, right? So we have we talked about like a normal distribution. We said if X is drawn from a normal distribution, it has two parameters, mu and sigma squared, right? These are the two parameters here, right? Mu and sigma squared. Those turn out to be exactly the mean and the variance. That's one reason the normal distribution is nice. It's parameterized by its mean and its variance. Okay, those are the parameters of this, distribution. We also talk about like an exponential. Distribution, right? An exponential distribution was, right, let's say, remember the normal distribution was like 1 over, what was it, 2 square root 2 pi sigma e to the negative, some value x minus mu squared to sigma squared. Okay, so that was the normal distribution. Okay, the exponential distribution, is described by this rate parameter, lambda, right? So this was where f of x was equal, oh man. I think it was lambda e to the negative lambda x. Okay, so, right, so there's this, I can describe the PDF just using this parameter, right? There's some input value it takes. Right, so this is f of random variable x at value lowercase x, right? This is the value that the PDF takes. I can describe that whole distribution, right? It's going to have some decaying property, right? This is the PDF f of x, and all I need to describe that is one parameter, lambda. That's what controls the shape of this distribution. Similarly, with the normal random variable, I'm going to have a distribution here, right? And it's described by the mean, and so the standard deviation. These kind of describe the whole, is all we need to describe the whole distribution, anything from this family. Okay. We also talked about like the uniform distribution. This one we won't talk about so much with like estimation. Let's say it's so A and B, and f of x is 1 over b minus a if x is in a, b, or 0 otherwise, right? So again, the distribution, I can describe it just by these. So 2 parameters, I get kind of the whole picture of what's going on just by determining these like 2 values, right? And so that's what makes these continuous distributions very nice. They're like parameterized nicely, whereas the discrete distributions, I need to basically define them as a table, right? And so it has a lot of, each element, potential element of the table is kind of like an own parameter, and it's much more complicated to describe those. These, a small number of parameters tells me exactly what's going on. Okay. So generically, we'll say I'll have x will be from a distribution, and it's going to have a parameter, so theta. Okay, so the parameters, right? So this value theta will be a generic parameter. Okay, when I'm talking generally about these continuous parametric distributions, I will just write it with respect to theta. Theta might be both mu and sigma squared. It might be kind of a vector of parameters. Okay, if I'm just talking about totally generically, we'll mostly talk about just one parameter at a time. Okay, so think of just theta as just one parameter, and to determine the distribution, we need to, once you plug in theta, then you get this whole kind of picture of what's going on. So, okay, so this brings us to question of estimation. Okay, this is the topic of this lecture. And by particular, what we mean when we say estimation is of a distribution's parameter. All right, so if you're doing like machine learning, you would call these learning of the parameters of your function class, or of your of the function which determines if you're doing like prediction. Okay, here we're thinking about it from a probability distribution point of view. You can actually derive most of machine learning techniques from this perspective. All right, we aren't going to do that, but just kind of I know that's what a lot of people are actually interested in. One of the reasons this is a prereq for taking all those courses. So, okay, so by estimation, what we mean is the estimation of the distributions, parameters, right? So how this process works is kind of in like, 3 steps, okay? Kind of 3 steps. You have to, so you either need to get, or, gather, or, have, some data, okay? So you want to go and get some data, or you have data, or you're gather, you need to collect data, right? These datas are going to be these observations, okay? Or these, like realizations, okay? So these are going to be like your lowercase x1, x2, up to xn. These are so lowercase. Okay, x's look kind of similar, upper and lowercase. Those are lowercase x's. Okay, so you're getting hard observations. Okay, you need to get some data. Then you have to choose a distribution. Okay, so I'm going to say when I'm estimating the parameters of a distribution, well, I have to have something to use to make the estimation. That's the data. But I also have to know what distribution am I estimating the parameters of, right? I need to say, do I think this is a normal distribution, or is it a chi-squared distribution, or is it an exponential distribution? When I estimate the parameters, I need to choose a distribution. Okay, so I've kind of given you the tools to do this, but we haven't spoken about it. So if I give you a bunch of data, like the data we looked at from like Old Faithful on Tuesday, how would you go about thinking about what was the distribution it came from? Maybe that one's a little tricky, but yeah. So you go to R and graph it. Great, yeah, that's exactly what you should do, right? Well, if you talk to so Gelman, there might be some confusion about this, but so the common recommendation is go to R and, so graph it, okay? So go and make a plot and look at it and say, that looks kind of like a normal, or that looks kind of like an exponential distribution, okay? This is kind of the common data science perspective on what you should do, okay? There are some statisticians who I actually kind of trust a lot, and I kind of, also feel this way, that there's also some reasons you should not do this, but we aren't going to get into those, so too much. Ask me after class sometime, and I'll go on some rant about this, or maybe with an extra lecture at the end of the semester. There's some tricky reasons why this can lead to like some wrong conclusions, but the other perspective, instead of this is what I was hoping you're going to say, and this is what kind of this class is telling you to do. Okay, so it's not like wrong. It's locally right. Right. So what is another thing you could do? You're going to choose a distribution, and I would say this might even skip step 0. Yeah.
Well, I would think if I already had a.
Yeah. So if I have a theory about the world, right? So this is like the scientific method approach. This is what you're actually like the root of statistics, what you're supposed to do. And you're actually supposed to do this first, right? What this one is saying is that this says that that this stuff should actually come first. Make a theory about the world before you collect your data. Okay, kind of data science, they teach you to do it the other way around, where you collect the data and then you kind of start looking at it and playing with stuff, and you kind of start to use the visualization to draw a conclusion, and then you verify that with estimation and other sort of like statistical tests. Okay, but the real classical theory of the scientific method, and we'll talk about this when we get into like Fisher's like original hypothesis test in a few weeks, is that you really need to make the theory first before you look at the data. Otherwise, the data can kind of bias you in ways that are going to be, somewhat unfortunate, and it could fool you into like the wrong conclusion. Okay, both of these together, I would classify as modeling. Okay, you somehow need to choose a model that you think the world follows, and there isn't like a tool from, maybe there are tools. I mean, the standard tools we learn here, the mathematical tools we're learning, don't give us clean answers to this, right? This is something you need to kind of use common sense reasoning to try and do. There's not like, oh, you sort the data and that tells you the answer, right? There's not like a computer program you can write to do this. You somehow need to think about what's going on. Either look at the data and think about it, or have a hypothesis or a theory about the world. Okay, yeah.
And then pick the best one.
Yeah. Okay. I mean, we've only done a few distributions in this class so far, right? But there are a lot of distributions, right? I could invent a new distribution if I wanted to, right? I don't know. Maybe I have invented a new distribution during the course of stuff I've done, right? It's not unheard of to invent a new distribution. It might be a little tweak on one of these, but there isn't like a limit of these are the only distributions it could, so possibly be. Okay, so in machine learning, this would be called like the function class you consider. Okay, so you kind of start by choosing, like if you're doing like, so deep learning, you build your neural net architecture and then you try and throw the data into it and see if what the data learns, what the estimation part, right? But you have to do that first. You have to choose the architecture. You choose what you think the world's going to look like. If you could say, well, I'm going to train multiple models and then see which one is best. But you have to choose which multiple models to train. There are a huge number of possible ways you could model things, right? So you couldn't just try everything, right? There might be kind of a short list of things you try, and that might be reasonable. But they might all give you answers. Say they all both. There might be two things that are similar that they both kind of look good. You can find the best in class of either of them, but you still doesn't say how one compares to the other necessarily. We'll kind of see that with hypothesis testing, but that'll mostly be comparing similar distributions against each other, or the same two kind of things from the same class against each other mostly. Okay. Finally, the topic of the lecture, you estimate the parameters, right? So this, you choose a distribution f of theta, and then you estimate the parameters theta, right? So I use the data somehow to estimate the parameters, so theta. Okay, yeah. The reason I started at 0 is, I had in my notes only steps 1 and 2, and I'm like, it's important to think about where that first step of gathering the data is. So I listed that. Typically, you might think of, you choose a distribution, then you estimate the parameters, and I kind of had more to say, so I added it as step 0. You could probably, have a step -1 that came before this. So it's always a question of like where you start, and it's the CS class. I'm allowed to start lists with 0, right? So yeah. So, okay. Although R starts with 1, right, which is a little confusing. So okay. Great. Okay, so then we want to estimate these parameters using the data, and that's what we're going to tell you a bit about how to do now. Just some fairly simple things, and then we'll tell you how good are those estimations. Okay, and they're a much more complicated way to estimate parameters, but we're going to give you kind of the probability and statistics view. Yeah, so good. All right. Well, except we aren't actually going to kind of estimate the the parameters, we're gonna reason about the estimation process, because this is on actual data, but we're in a probability and statistics class, so we're gonna talk about the random variables, which is gonna say, what if we did estimate it this way? How good would it be probabilistic? Okay, so now we need to go back to say, think of, we have these random variables, x1, x2, up to xn, and we're assuming they're IID from some, so at this point, we're from some distribution. We're in step 2 now, right? We've chosen, we maybe have our data, maybe we don't have the data yet, right? And that's another reason why it's maybe not there. We're still thinking about if we had data. These are random variables, and so they're uppercase x's, and they're from a distribution. We've chosen the family of distributions, and there's some, let's say there's one parameter now, theta, that we want to estimate. What is a good choice of theta for that distribution given the random variables? How would we do that, right? And so what we're going to do is we're going to create an estimator. Okay, an estimator. I'm going to put a hat on my theta. When I put a hat on it, right? This is a hat means it so estimates, right? So if you wear your like estimation hat, then you're estimating something, I guess. Okay. And this will be defined as a statistic, okay? x1, x2, up to xn, right? So there's I take in these random variables, I do some function, I'm gonna compute some function on the random variables t, and the outcome of that function will be a value. Again, this is a random variable, theta hat, and that is my, estimator. Okay, I'd like my estimator to hopefully be close to usually in a probabilistic sense, to the true value theta that the data was drawn from, that describes the process with which the data was drawn. Okay, so what would be a good property to have of the random variable theta hat with respect to the true parameter theta? What would we like to have? Yep, a match. Okay. Well, we already have a mismatch of a type, right? We can't totally. Oh, what do you mean by a match? This is a constant, and this is a random variable, right? So that means I've got a probability distribution of f of theta hat, right? It has its own PDF, whereas theta is a constant. So yeah, I'd like a match, but how would I use my probabilistic language to say I would have something like a match? Yeah. Great. So perfect, right? I can talk about the expected value of theta hats, right? It's a random variable, but if I want a single number representation of it, the expected value is pretty good, right? So if I want that the expected value of theta hat is exactly equal to theta. So this is what I want. There's some cases you actually, probably won't get too much into. You don't always want this exactly, but this is pretty much a usually a desirable property. Okay, so this means this indicates that this is an unbiased estimator. Okay, so I can say theta hat is an unbiased estimator of theta if the expected value of theta hat is exactly theta. Right? And in fact, I can quantify, I can say that the bias of theta hat, this is a, so a term here is going to be the expected value of theta hat minus theta. Okay, so if the bias is 0, then it's unbiased, right? So an unbiased estimator has the bias 0. That means that the expected value of theta hat, which is theta hat's a random variable, is exactly the parameter, so theta. Seems like a nice SOAP property to have. Okay. Have we seen any unbiased estimators so far that you can even think of off the top of your head? Yeah. Yeah, the mean, right? So you're thinking of, and this is the example I wanted, right? So an example, if we have, let's say that the that the data that x1 through xn is IID from a normal distribution theta, and let's just not worry about the variance, say that's 1. It could be anything. Okay, and I create a statistic T of x1 through xn is going to be defined as 1 over n, I equals 1 to n of xi, right? So this is, I'll call this, we call this x bar n, but I'm going to call this mu hat. Okay, this was x bar n before, but I can call this mu hat. Let me move this around. So on this side, let me call this mu hat. And on here, we'll say, yeah, this was x bar of n. Okay, and we can say that this is going to be biased because the expected value by the central limit theorem, right? This is exactly mu. We can use the central limit theorem, tells us that the average is an unbiased estimator of the mean of a distribution, right? It doesn't have to be the normal distribution, but kind of, for example, any distribution where the parameter we want describes the expected value, right, of that distribution, then so we can get an unbiased estimator by taking the mean. Yeah, okay, good. So this is good. This is an unbiased estimator. So great. So this notion of bias tells us, if we could create another estimator which has a bias. Okay, and so in the rest of the lecture, there are kind of two things I want to do. One is I want to show you an estimator for the variance of a normal distribution that's going to be so unbiased. And we'll see kind of something that you might have guessed would be the right statistic and show that that statistic has a bias. Okay, that'll go through some calculation. So let me tell you the other part of it first. Right. So the other thing I want to do is to talk about the like efficiency of an estimator. Okay, and then we'll go and talk about an unbiased estimator for the variance. Okay, the efficiency of an estimator tells you, it's something about telling you how good is the estimator. Okay, so I could have two different functions, T1 of x1 through xn, and T2 of x1 through xn. Okay, and this will give me an estimator theta 1 hat, and this will give me theta 2 hat. Okay, and I might be able to say that expected value of theta 1 hat is going to be equal to the expected value of theta 2 hat is going to be equal to, so theta. Remember, x1, xn is drawn from some distribution, parameterized by so theta. So they're both unbiased estimate, right? So they're they could both be so unbiased. Okay, so okay, if I can come up with two unbiased estimators, I want to quantify which one is better. Are they both equally good if they both have the same expected value? Maybe one is better than the other, right? So I want to talk about what's known as the like efficiency of the estimate. All right, if you go, I want to say, let's go with the example of the mean again, right? Let's say the example is that I want to estimate that theta is equal to the mean, and I know that xn bar, I can call this so theta 1/2, right? This is taking the average of all of our data, and I know that this is this one's going to be unbiased, right? There's another much simpler estimator which is also going to be unbiased. What's another simpler estimator that's also unbiased, right? We want something with the expected value equal to mu. Take the average the old-fashioned way, right? Well, that was like, this was defined as so the average, right? So this is xn bar is exactly the average, right? So that's I don't know what the old-fashioned way of taking the average. Maybe you're like, oh, you know, back when Professor Phillips was at school, they would take the average that old way, but oh, yeah. What we aren't going to worry. We're in the land of like probability, not in the land of computation. And we're not worried about like numerical stuff or efficiency of how long does it take to compute. Those mathematically, those can be algebraically reduced from one to the other as the same thing. All right. So land where we can do algebraic equivalence is what we're thinking about. So it's much easier than that. Yeah.
Maybe the
median. Yeah. Okay. In the normal distribution or even the uniform or any sort of like symmetric difference, the median is going to work here, but I haven't necessarily, so said that here. I could have something like the exponential distribution, and I say my parameter is 1 over lambda instead of lambda, right? And so the mean is 1 over lambda, and then I need to, it's not symmetric, so the median's not going to work necessarily here. Even simpler. You're thinking something much less complicated. Even so complicated, you're thinking, oh yeah, you're gonna. If we look back at the central limit theorem, I need something where the expected value is equal to mu. Do you see anything up here else that has expected value equal to mu? Yeah. Yeah, right. I can just take x1. I can say that theta 2 hat is just going to be equal to x1. I just take the first data point I get. So I'm going to ignore the other data points. I'm just going to look at one of them, right? It's unbiased, right? It's not going to give me a biased estimate. So this is also unbiased. Okay. So is this a good one to use? Maybe from a computational perspective, it's more efficient, right? So maybe you could argue that, but that's not the efficiency we're talking about here. We're talking about like statistical efficiency. Which one do you think is better? Xn bar or just X1? Okay, I could factor them in. Yeah. But how is that helping me? Why is that better?
So XN, the lower variance.
Great. Very good. Very good. So the variance of Xn bar or is going to be less than the variance of X1, right? This one has a variance of sigma squared. This one is sigma squared over n, right? So this one is, promise I wrote n up there. It's going to come in a second. Okay. This one is more efficient. Right, so this is more efficient because the variance is less. Right, so if I have two things with the same expected value, but one has a lower variance, then that one is a more efficient estimator, and that tells us it's a better estimator. Okay, so if I'm creating an estimator, the two things, kind of the two kind of standard goals of so parameter estimation. Parameter estimation. Okay. The first one is small so bias. And if bias equals 0 means that it's going to be unbiased, which is great. That's so kind of like the gold standard. And the second one is I want small so variance, right? Okay, so often you can get bias 0, and then if you can get the bias 0 so it's unbiased, then you want to say I want the estimator that has the smallest possible variance given that it's unbiased. Sometimes, kind of beyond this class mostly, I think you'll want to trade off. Maybe you could reduce the variance by increasing the bias a small amount. And sometimes that's a useful thing to do. You don't want to increase it so it's like, if the variance is really small and the bias is large, well, you're getting a very kind of confident answer about something that's wrong. You don't necessarily want that, but there are other kind of, sometimes you want to trade this off, but typically in this class, we'll want an unbiased estimator and a small variance. That's what we're going to be trying to aim for. Yeah. Yeah, if you know what the bias, if you can calculate what the bias is, then you can fix it. You can fix it afterwards, right? Sometimes you're like, oh, it's actually computationally more efficient to compute this other thing, but I know it has a bias. Sometimes what you do is you then estimate the bias and you get the expected value of you estimate the expected value of the bias, and then you subtract off the expected value of the bias, right? So sometimes you'll do something like that. That's a way to get, ultimately that will give you an unbiased estimator set. Right, so there are these more advanced things you can do, but they'll be outside the scope of this class, I think, unless we get into them at the very end. Yeah. Okay, so you want bias 0 typically, and we want small variance. Yes. Okay. Great. Okay. Okay, there's one more thing I want to talk about this lecture. Good, we're doing good on time. Is I want to remember if X is from a normal distribution, it has two parameters, mu and so sigma squared, right? We talked about an unbiased estimator for mu. What we didn't talk about was, in this lecture, was an unbiased estimator for so sigma squared. Remember, on Tuesday, we did define something called the sample, so variance, this is defined as Sn squared 1 over n of the sum from I equals 1 to n, xi minus the expected value of, or well, actually we did it this way, xn bar squared. Except it was slightly different. There was -1 here. Okay, and this was, I told you, this was a little bit kind of strange sight to see. So we're not taking the average deviation from the estimate of the mean, but right, because we're taking 1 over n minus 1 times the sum of the squared deviations from the estimate of the mean. Okay, if we knew the exact, if we knew the exact mean, if we knew mu exactly, then you would do 1 over n instead. But because we're also need to estimate the mean, you need to do the divide by, so n minus 1. So I mean, what I'm going to show you is that this is a unbiased estimator of the variance. Okay, I'm going to claim, so I'm going to show you is that I can say this is sigma squared hat, and the expected value of sigma squared hat is going to be, let me put it up here, that this is going to be equal to sigma squared. Okay, so if I create this so statistic, right, which is a random variable, that it's going to be an unbiased estimator of the variance. Yeah, so okay, but if I did a 1 over n instead, then it would be a biased estimator, and we'll see that. Okay, so I'm going to kind of the next 10 minutes or so, I'm going to kind of walk through this argument, and then we'll do a summary of what you need for the quiz. Okay, we'll start with a couple of properties, and then we'll do some derivation. I think it's useful to kind of, so to see this, you'll probably be seeing this on Wikipedia and the textbooks for the rest of your life, and if you don't pay attention now, you'll always wonder why I needed the n minus 1 instead of the n. Okay, it definitely bothered me until I, actually, so saw or actually worked through this derivation. All right. Okay. So if I just look at, again, we're going to have these NIID kind of so samples, each of these XI IID. And so I know that the expected value of XI is equal to the variance of XI plus the expected value. It's actually expected value of XI so squared plus once you factor it equals this sigma squared plus so mu squared. This is a fact I will need. Okay, I will also recall that expected value of n bar squared. Okay, this is going to be equal to, I can write this as the variance of xn bar plus expected value of xn bar so squared. Right, when I square it, I need to look at all of the so the it's actually a sum, and if you expand out the sum, or you can think of it as the expected value of, right, this one is actually the expected value of xn this. So so I want to skip to this. Oh, okay, I thought I had in my head, I thought I had a simple reason to tell you why these are, but I've forgotten that now in the middle of the lecture, but we're going to state these properties as fact. You could so derive these. Okay. And from here on out, we're going to drive everything from first, so principles. Okay. So we also need the expected value of xi times xn bar. Okay, we're going to write down these facts, and then we're going to write out the expected value of Sn squared, and we're going to kind of expand that, and we're going to plug these things in to see where the n minus 1 comes from. Okay, this is equal, I can expand out xn bar here. This is xi times 1 over n. I equals 1 to n of xi, let's say j here. Okay, and I can now, by linearity of expectation, I can push through the 1 over n in the sum. And I get expected value of xi times xj. Oh, okay, and now I want to look at what is this guy here. This guy is expected value of xj, xi. This is equal to the covariance, right? It's a joint distribution of xi and xj plus the expected value of xi times the expected value of xj. Okay, so if I is not equal to j, then the covariance is going to be 0. So then this is equal to mu squared, because they both have expected value mu, and so the covariance is 0. Okay, so now I can go back to this term here. Okay, and now we can say, well, if I sum over these things, for most of xi and xj, there are n things where I is not equal to j, right? And so those, the average of those is going to be mu squared. But when there's one term where I is equal to j, and so that's going to be sigma squared over n. Then the covariance when I is equal to j, if I is equal to j, then the covariance is going to be the variance, the covariance of xi, which is the variance of xi, which is sigma squared, right? So of the n terms I'm summing over, n minus 1 of them are going to be, or exactly mu squared, and one's going to be mu squared plus sigma squared when I get xi. And so in that case, but I'm dividing by n. So that one, I get mu squared plus sigma squared over n, which ends up being the same thing as so this term. Okay, if I do xn bar squared, I'm going to be kind of doing this step n so times. I'm averaging n versions of this of like the third bullet. For each xi, I have two sums in xn bar squared, because there's xn bar times xn bar, and I write two sums, and each of the sums looks like that so third bullet, and I'm averaging over each of those, right? And so they, so on average, they turn out to be sigma squared over n plus some mu squared. So that's, so you kind of reason from the third bullet to get, in order to get this one. Ends up being the same. Whereas if I just have xi squared, right, I'm just going to get this. It's just it's just because I just get the variance every time. Okay. Okay, so I need these three facts, and we'll have to remember these. Now I want to expand expected value of Sn squared. Remember, this is going to be the expected value of 1 over n minus 1 times the sum of I equals 1 to n of xi minus xn bar squared. Okay, so the first thing I can do is use linearity of expectation, n minus 1 times the sum I equals 1 to n, right? And I get back inside of here xi minus xn bar squared. Okay, next I can expand this, n minus 1, I equals 1 to n. Now I've got, going to have three terms here. I have xi squared minus 2 xi xn bar plus xn bar squared. Right, just expanding that sum. Okay, n minus 1. And now I can look at each of these individually, again, by linearity of expectation. And I have all of these, so values now. I calculated all of these on the previous slide. So I'll plug these in. Okay, so these were, the first one was mu squared plus, so sigma squared, right? Now I had minus 2 times mu squared plus sigma squared over n. Is that right? Yep. Plus mu squared plus sigma squared over n. Okay. And what we can see is that the last two terms have some cancellation. The mu squared plus sigma squared over n occurs twice. So I'm going to cancel this out, right? There's minus 2 of them plus 1 of them, right? So now it's just minus that one term. And now what's left, I have, now I can cancel out also the mu squared and the mu squared. Okay, and what's left is going to be n minus 1. What I have, sigma squared minus sigma squared over n, right? Which this is equal to sigma squared of n minus 1 over n. Okay. Now each of the terms in the sum is the same, right? So I'm going to have n terms in the sum. That's going to cancel out the n and the n minus 1, and so you can get exactly so sigma squared. Oh, great! This is what we wanted, right? This means that this implies that S squared is Sn squared is an unbiased estimator of sigma squared. Okay, so it's kind of because we're also estimating the mean inside of here, because that wasn't given to us. We had to estimate it with xn bar, that we ended up dividing by n minus 1 instead. If we had instead, if we had looked at, let's say, sigma squared hat, let's call this n, right? If we instead looked at 1 minus n expected value, 1 minus n times xi minus xn bar, right? This would also be an estimator of sigma squared, right? I put a hat on it. It's an estimator, but the expected value of sigma squared hat n, right? I know that this is going to be n minus 1 over n sigma squared, right? So it's off by this n minus 1 over n factor. Okay, so that means this has a bias. So I can say that the bias of sigma n squared hat is going to be equal to sigma squared over n, right? So that's sigma squared minus the expected value. So it's going to have a bias. So it's not unbiased, right? So it's not 0. So not on. So it's not unbiased. Okay, so that's an example of a bias estimator. It's not very far off. As n goes to infinity, it gets closer and closer to the right value. So it's not too bad. If n's really big, the bias is pretty small. But you can tweak it a little bit and get an unbiased estimate. So, okay, great. Okay, good. So let's do a quick review. Okay, there kind of the two things to review this week. Let's say IID means identical and dependently so distributed. Okay, that means that they're all from the same distribution and they're going to be independent of each other. Okay, probably 1. 2, if I have x1 up through xn, and these are IID from some unknown distribution, and I have the expected value of xi equals mu, and I have the variance of xi. Expected value is equal to mu. The variance is equal to sigma squared. Then xn bar has the following properties. Let's say A, that the expected, where xn bar, remember, is the average, is the expected value of xn bar is equal to mu. The variance of xn bar is equal to sigma squared over n, and that this is B, and C, that in the limit as n goes to infinity, then I have that, let's write it in this way, Zn, which is going to be equal to x minus mu divided by sigma over square root n. This is going to be distributed by a standard from a standard normal distribution. Right, there are other ways. You basically need to know that in the limit from any distribution you start with, and you take the average of the random variables, it will converge to a normal distribution, right? With expected value mu, the original expected value, and the original variance divided by n, right? And if you do this normalization, this z variable that will show up a little bit later in the semester, it converges to a standard normal distribution. Okay. Okay, and then 3 would be about, so this is called the central, so limit, so theorem, right? The CLT, okay? And the third one would be about what we talked about today, estimation. Okay, we're going to get some parameter estimation. So actually, the talk about how you have to model the problem, and you have to do that, and then you can pick a parameterized family before you estimate the parameter. That's also really important, but it's kind of a little bit harder for me to easily evaluate you for that in the quiz. But as important knowledge goes, that's going to be, so like important knowledge. Okay. The bias. So if you calculate this a statistic, this is a statistic, right, from these data. The bias of this is going to be, make sure I say this consistently. This is the expected value minus of this estimator, minus the true parameter you're trying to estimate. Okay, so this is the bias, and I'm going to say if bias equals 0, then I say it's biased. Okay, we would like unbiased estimators of the parameters. If you can estimate the parameters and you have a guess of what the distribution is, it tells you, okay, this is a good model for where the data came from. That's simple to describe and hopefully easy to understand. Yeah. How do you know how far you are from the true parameter? That's a great question. If you have a bound on the variance, you can say something like probabilistically, right? The expected squared deviation from the true value is the variance, right? So that's one way to quantify it. There are other ways to quantify it, and we will try and talk about these. That's kind of what, that's something like what confidence intervals and hypothesis testing, which will be the next two topics, will be about. How to quantify, is this close or is this far? How give a probabilistic way of describing this, other than just talking about the variance. The variance is kind of a pretty easier to understand tool, but there'll be other tools which will give us a little bit more precision in how we answer that question. And that'll be what most of the rest of the semester will be about. So that's a very good question. Yeah. Yeah, X bar, yeah, good to, I'll try and define it every time I use it in a question or on the homework. But X bar N is always going to be the average of the sample random variables, right? I get IID random variables sampled from a unknown distribution. X bar N is going to be the average of N of those random variables, right? And that's what the central limit theorem is about. And it turns out to often be a good estimator for the mean of the distribution. All right, great. Well, let's stop there. So the quiz is now open. I won't be able to stick around too long after class today. I got some childcare stuff. Yeah, question. Oh, that's X minus U. X minus U. Yeah, thanks. Over square root N. I'm dividing by the standard deviation, right? Yeah. Let me turn off